Hey folks, in this video we're going to talk very briefly about electrical instruments, or briefly about each instrument. The whole thing may not be brief, but we'll briefly talk about some electrical instruments. So number one is called a galvanometer. And we will talk more about this when we get to magnetism. But basically, the idea is very simple. You have a coil of wire in this object, and when current runs through the coil of wire is in a magnetic field, a permanent magnet, and the wire will rotate. So if there's a little needle, the wire will rotate based on how much the more current that flows through that coil, the stronger that little electromagnet becomes, the more it interacts with the big magnet, and the more the needle rotates. So it's a way to measure current. And again, we'll talk more specifically about that magnetic force and such when we talk about magnetism. But for now, that's all you got to know. It's a thing that moves it's a thing that moves if you run current through it. Now, there's lots of ways to use that. One way is as a voltmeter. Okay, so a voltmeter is a galvanometer, but it has a certain resistance to it. Now, when you hook up a voltmeter, let's say you have a battery or power supply, and let's say here is your resistor. If you want to know the voltage across the resistor, you hook up the voltmeter parallel to the resistor. Now, a key rule about meters, you don't want the meter to affect the thing that you're measuring. So if current's coming out this battery, you want that current to keep going through the resistor. You don't want a lot of current going through the voltmeter. A teeny bit has to go through the voltmeter for it to work, but you only want a teeny bit going through the voltmeter. So how do you make it so most of the current keeps going through the resistor? Well, you give the voltmeter a very large resistance. So you make the galvanometer, but you make it have a very, very large resistance. So only a teeny bit of current will be siphoned off to the voltmeter. And that's how you measure voltage. An ammeter is kind of the opposite. Now, an ammeter is still a galvanometer, but when you hook an ammeter up, you want it to be in series with everything. You want the current to go through it to measure the current, but you don't want the ammeter to affect the current. So an ammeter is simply a galvanometer with a small resistance. Okay. So that's the difference between a voltmeter and an ammeter. A voltmeter has a large resistance, so current won't go through it and affect the current that's already going through the circuit. An ammeter has a small resistance for the same reason. You don't want to affect the current that's already flowing in your system. The next quick thing I'll talk about is called a Wheatstone Bridge. Okay, so a Wheatstone bridge is a way to determine an unknown resistance if you have three resistors that you do know the resistance of. And so here's what you do. Let's say you have the four resistors, one unknown. You hook them up in a diamond pattern like so. Okay, so like this. And let's say we'll call this one R1, we'll call this one R3, we'll call this one R2, we'll call this one RX. And that's the one we don't know, RX, okay? So let's say R1 is a variable resistor. That's also called a potentiometer. So let's assume that you can adjust that resistance. So it'd be very much like adjusting a dimmer switch for a light. What you're doing there is you're just adjusting the resistance of the light. Well, what you do is you hook this up to any power source, battery or anything, okay? And you run current through it, and you hook this up with either a voltmeter or an ammeter right there between A and B. We'll call these A and B. And you adjust your R1 until that voltage or that current reads 0, okay? Now, if that current reads 0, then we know the following. We know that the voltage drop here has to equal the voltage drop there. Now, we'll call this current I sub A, and we'll call this current I sub B. So the voltage drop of R1, which would be IA times R1, has to equal the voltage drop of R2. So that would be IB R2. Okay. Now again, you've adjusted R1 until there's no voltage difference between A and B. Therefore, the voltage drop of R1 will have to be equal to the voltage drop of R2 because you've adjusted that voltmeter, or you've adjusted R1 until that voltmeter reads 0 volts. So there's no difference in voltage between points A and B. Now we also know that if there's no voltage difference between points A and B, the voltage difference of R3 and of Rx has to be the same. So you get IA times R3 has to equal IB times Rx. Well, if you, let's say you solve for IA right there, which would be IB Rx over R3, and you sub that in right there, the currents would cancel out, and you'd get the following relationship. R1 over R3 equals R2 over Rx. Or solving for Rx, Rx would be R2 R3 over R1. So that's a way to determine an unknown resistance if you only have one meter, you only have a voltmeter or an ammeter. Well, then you can use this method to determine an unknown resistance. The last thing I'll briefly talk about is household wiring. So for household wiring, now for this discussion, we're going to keep it really simple, okay? So you're going to have either in your house a circuit breaker or a fuse box. If you have a modern house, it'll be a circuit breaker, okay? And if you could see behind that circuit breaker, more or less what you'd see is you'd see three wires coming into your house. Two of them would have current, and one would be a neutral wire. That eventually goes to the power company, eventually goes to the ground. Okay, so in this case, we'll say this one is neutral and this one is hot. Okay, now on the other side, you'd have another hot and another neutral. Okay, like that. All right, so we'll just focus on one side of your circuit breaker. So what you would do then is you would have wire running from the hot throughout your house and wire running from the neutral throughout your house. Now, these wires would be in something called conduit. So this blue would be like a metal pipe, and it's called conduit. We'll talk about that in a second. Okay, so then let's say you've got yourself an outlet. So let's say your outlet, it looks kind of like two prongs, and there'll be a thing like that, and it looks like this. Okay, and then usually they come in pairs like so, right? Two plugs like that. So what's going on behind the wall there? Well, one wire is going like that, and that was the neutral wire, and the other wire is going like that. Okay, now these are wired in parallel. Okay, so if you hook something up to one of the plugs, the other one still works just fine. You're not interfering with the other one. So your whole house is wired in parallel. So you can add as many things as you want, well, within reason, and they won't affect each other. If your house was wired in series, that would be a huge problem. You unplug one thing and everything dies, right? So your house is wired in parallel. Okay, so if you plug something in, like a toaster, let's say, okay, so there's your toaster. Well, the current flow of electrons comes from the hot wire through there. It would go down through your toaster and then back to the ground through the neutral. Okay, so that's how something like a toaster or a flash or a light or a lamp or anything like that would work. Okay, so there'd be a resistor in here, or some other heating element or something, or like a fan, it would be an electric motor, but same idea. Okay. Now, what's that third prong about? What's this third plug about there? Okay. Well, that's called the ground plug, and it's a safety thing. If you could look behind the wall, that is connected to the metal conduit, okay, somehow, either via a wire or it's screwed directly to the metal box, which is then directly attached to the conduit. That conduit is attached to your circuit breaker, and your circuit breaker will have a copper strap or some other piece of metal that is eventually attached to either a water pipe or a gas pipe. And both your water and gas pipes go to the ground. And no, it's not dangerous to hook this up to a gas pipe. In fact, in my house, that copper strap is hooked up to a gas pipe. So here's the idea. Okay, so let's say you got your toaster, and your toaster has that ground plug, like so. So it'd be hooked up like that. And let's say the wires, and let's see what color, I guess I'll have to use red. So let's say the one wire goes like that, and then the other wire goes to the other plug. Let's say something goes wrong, and this wire gets frayed and touches the toaster oven or the toaster box, the metal box that's surrounded it. Well, now this toaster box is live. Okay. Now, if it stayed that way and you touched it, that could be dangerous. You could electrocute yourself. Okay. So here's what happens instead. When this wire, let's say this wire gets frayed and touches the box, well, then a lot of current flows because your resistance is very, very low. So a lot of current will flow through this wire into the ground. Okay. Now, your circuit breaker, you have a circuit breaker here. And the circuit breaker, what it does is if it detects a current that's too big, the current shuts off. It shuts the current off. So if your current ran through this toaster case, there'd be a lot of current because your resistance would be awfully low. And so that huge amount of current would flow for an instant, and then your circuit breaker would say, and it would shut the current off totally. And so then if you touch the toaster, it wouldn't hurt you because the electricity is now shut off to that part of the circuit. So then you would so then your circuit breaker would trip. You would unplug your toaster. You would go down to your basement or whatever. You would put that back in. And then before you plug your toaster back in, you would figure out what exactly went wrong in the toaster to cause it to ground like that. All right, so that's a very, very, very basics of electrical wiring in your house. There's a lot more to it than that, but that's the basics, and you can actually get pretty far just knowing that. All right, I hope that video was helpful, and thank you very much.